Go ahead.
Okay, welcome everyone. Welcome to today's HAO colloquium. Today our speaker will be Mei Zhang from National Astronomical Observatory of the Chinese Academy of Science. So Mei Zhang is a senior scientist in the National Astronomical Observatory of the Chinese Academy of Science and is also a joint professor in the University of the Chinese Academy of Sciences. She obtained her bachelor degree from Peking University in 1987 and her master and PhD degree from Beijing Astronomical Observatory of the Chinese Academy of Sciences in 1990 and 1999, respectively. From 2000 to 2004, she worked in HAO first as a long-term visiting scientist and then as a project scientist. Upon her returning to China to take up a professor position in the National Astronomical Observatory, she becomes an affiliate scientist of HAO since 2004. Her work covers topics on coronal modeling and observation, magnetic field measurement and observation, and more recently on solar interior dynamics, which is also the topics of today. So today, Mei will give a presentation titled "Simulation of the Convective Dynamo in Solar Convection Zone: The Role of Small-Scale Magnetic Fields." So welcome, Mei. Go ahead.
Yeah, thank you. Thank you for the introduction. And so it's my pleasure to be here to give this talk. And so today, I will talk about basically two topics. And the first one is the role of current helicity in driving solar dynamo. And the second one is about the mean field coefficients extrapolated from the dynamo simulations. These are two papers I'm in prepare. But actually the work it's done many years ago. So the first part of the work it was done in 2016. So with Yuhong, and so I already presented this result in a few meetings. So just list a little bit. So if you have heard about this talk, so I apologize for repeating it here. And the second part, the work was done in 2018, also a long time ago. And this I only presented in a group meeting. So maybe most people haven't heard about this part yet. So basically, what those work I presented today is all done during my visits as a field scientist of NCAR and here. So I would like to take this chance to thank all my hosts of my field scientist visits. So first for BCA Law for almost 10 years, more than 10 years, and then Mark Misch, and then Yuhong Fan, and also Sarah Gibson. So this work mainly was done mainly during the years when Yuhong was my host and host, but also have some contribution from Mark Misch because I talked to him a lot, and also he provided some analyzing ideal programs. So I would like to thank all these my HL houses and for my visits. And so the topic of today is about the solar dynamo. So we all know that the main objective of solar dynamo is to understand the origin of solar magnetic field and its behavior, solar cycle. So basically, we need to understand, why the sunspot behave like this butterfly diagram, and maybe more importantly, how this magneto butterfly diagram, why it works in that way. And but for dynamo problem, so basically we have two approaches. So one is the we call it DNS, the direct numerical simulation. So basically, we solve the full MHD equation. So just you have this is a full MHD equation, and it has advantages is for this approach that is fully dynamic, and so we solve the full MHD equation. There's some assumption, but not that much. And this is the advantage. And but the disadvantage of this approach is that it is computational, it needs a lot of computational resources, and so basically we cannot, simulate it for too many years. And like what we do with Yuhong and maybe hotter suns, we only simulate for 50 to 100 years to 100 years. And another approach is about what the traditionally we use the mean field theory. Basically, we only solve the induction equation only. So, and we decouple the magnetic field as the large scale and small scale, and then the small, to solve the large scale, okay, comes. So we basically only solve this equation of the large scale magnetic field, Then you see here the small field comes into as the parameters, like this alpha and beta as the parameter. So this advantage of this approach is that it is computationally very economic. So you can simulate for millions of years. But the disadvantage of this approach is that we have to basically prescribe the coefficients like this alpha, beta. Like traditionally we prescribed in this way. This alpha coefficient is related to the kinetic helicity, and this beta effect related to this kinetic energy of small scale velocity. So basically that means it has a lot of either explicit or implicit assumptions in this approach. So basically what I'm trying to do is that I would like to sort of connect these two approaches, to understand our dynamo problem. So the first part is I call it the role of kinetic helicity in driving solar dynamo. So basically this is try to understanding the MHD dynamo simulations in terms of the mean field coefficients. So I started of my study with the dynamo problem from 2014 after this Yuhong published this paper. So I think at that time, this paper was the first simulation that using the solar rotation rate and produce this polarity reversal and self-formation of flux slope, and also produce this solar-like differential rotation. So it is quite impressive at that time. So then I go to Yuhong, approach to Yuhong and ask her to give me her simulation data so to analyze. So why I do that? So basically it is because I did some observations about the photosphere current helicity and study. So basically from that we know that so this is a paper from Pipsos. So basically we know that so this is the latitude, this is the latitude, and this is the current the twins or current helicity, so whatever. And so basically we found that in the northern hemisphere, statistically the current helicity or twins is the negative, and in the southern hemisphere is the positive. So I just dig out Yuhong's data and I calculate all these current helicity and the twins and all these numbers, and I found it goes with observation quite well. So you see here in the southern hemisphere is not all, it's statistically positive, and in the northern hemisphere it is negative. So I feel very comfortable with Yuhong's simulation because I think it goes with observation. Then I said why I want to use her numerical simulation data, because it tell me much more information in the simulation than the observation. For observation we only know one layer, that is the photosphere, but here I can go to all the way deep into the solar internal and to see what's the current helicity pattern. Then I found it's very interesting. You see, here this is near the surface, and when you go to the deeper and the deeper, then it actually changes the sign. So you see here near the surface, it is the positive in the southern hemisphere, negative in the northern hemisphere. Then if you go to the deep layer, it changes sign. It is negative in the southern hemisphere and the positive in the northern hemisphere. So originally I had to try to use this result to interpret one of our observation. Basically, in our observation, we found that the like take this for example, is a sunspot, and this is the ambular, and this is the perambular. So we found that this is the current helicity map. So you see here, the current helicity is positive in the ambular and is negative in the perpendicular. So if you look at this, so this is R from the center of the sunspot. So it changes the sign. So that means all observation says that the strong field actually have a strong field and the weak field have the opposite helicity sign. So I had to try to use this to interpret our observation. So maybe the central part of the sunspot, that where the field is strong, comes from the deeper layer, and the weak field comes from the more shallow layer. So then I also calculate all this kinetic helicity, because I can do that, because I have all this numerical simulation data. Then I found the kinetic helicity also, this near the surface, it is also positive in the southern hemisphere and negative in the northern hemisphere. It also changes the sign to the when it goes to the deep layer, but it changes at a relatively more deeper layer. Then I plot off all this. So all this is here. So this is the current helicity, and the bottom one is the kinetic helicity. So you see here they change the sign here. This changes the sign here, and this one changes the sign here. So and note here, near the bottom of the convection zone, so they actually have the same sign again. So near the surface they have the same sign, and but at the bottom they also have the same sign. So but it's different from the surface. So basically that's what I did the first year when I worked with Yu-Hong. So I could be very happy at this moment to using her numerical simulation data to interpret my observation. But then the next year it comes this paper, this Hideaki-san's paper in Science. Basically, this also very impressive simulation. Basically, what they found is that if from this their paper A, B, C, from A to B to C. So actually this one they call the case low, and this they call case medium, and this called case high. So from low to high, the Reynolds number increases. So the Reynolds number increases. You see here from this 300 something and all the way to high case is nearly 2000. So but they found that with the increase of the Reynolds number, actually the large scale dynamo first appear and then disappear and then reappear again. So basically in their paper they said this is the mystery large scale magnetic field. So disappear first and then recover with the increase in Reynolds number. So then this I think this I already know this result in 2015, and Hideaki-san presented everywhere, and it's very impressive. But then I realized what? So this animal case paper. So animal case paper. This paper is already published in 1976. Basically, what they say is that in a strong MIT electric turbulence, the alpha effect in a nonlinear dynamo is determined by the difference between a purely kinetic and a purely magnetic helicity term. So basically, traditionally we only consider the kinetic helicity term, so like this one. And but they point out that actually this is another term. This is called the current helicity term. So notice that here this is the plus and this is minus. So that means it is determined by the difference between these two terms. So note, previously we showed that at the bottom of the convection zone, and so where we believe that the dynamo is initiated, created, and so basically at the bottom of convection zone, so these two has the same sign, but the really alpha coefficient is actually determined by the difference between these two, right? But originally, I think this, this paper published so long time ago, and but why it doesn't take much attention to the community, because most people think that the second term, the current helicity term, is small, so the magnitude is small, it's not dominant. But because I have Yuhong's simulation data, then I plot out these two terms. So you see here, the blue line is what comes from the current helicity term. So it's actually divided by rho, so this term, and the right line is the kinetic helicity term. So it's like this one. So you see they have the same sign, but because this has a minus sign here, so actually the real alpha, so real alpha is the difference between these two. So here you see that the blue line is actually above the red line, right? So that means the current helicity term, so this term is actually dominant over this term. So the real alpha, if you might get the difference between these two, is this black line. So you see here, so it's this line. So that means, so you can see that the resultant alpha is actually determined, has the same sign as this current helicity, right?
Question: how strong is the magnetic field compared to the velocity when you do this? Are they comparable, or is one much smaller? Are we still in a?
You mean it is a little you mean energy or current? The energy is comparable. So yeah, energy is comparable, but here is the current helicity and the kinetic helicity.
Yeah.
So that's difference. So I will talk about this later on. So yeah, so that's the difference between these two. So okay, so here that means actually your sign is determined by this current helicity term, and the current helicity term is already larger than the kinetic helicity term. So this is Yuhong's paper in 2014. And later on, Yuhong and Fang, they have another paper published in 2016. And so the difference between them is whether the result is implicit or explicit. But basically, the real difference is that in the 16 paper has a larger Reynolds number. So this is what I calculated. So the Reynolds number in this simulation is this, and the Reynolds number in 16 simulation is this. So basically, then here you see here also again the blue line are the current helicity term, the red line kinetic helicity term, and so this solid line is from the 16, and the dashed line is from the 14 paper. So you see here with the increase of the Reynolds number, actually the current helicity term becomes larger and larger, larger. But the kinetic helicity term, the kinetic helicity doesn't change very much. So its change is very moderate. So that means with the increase of the Reynolds number, so the current helicity term becomes more and more dominant, right? So from this analysis, then I realized, how can this hot zone they produce their kinetic disappear or repair? Because I said, what happened if the current helicity decrease further? So here from Yuhong's 14 to 16, they go in this way. So then I asked Yuhong, so what happened if we go in the opposite way? So let's go to the lower Reynolds number. Then if it decreases further, then at some point, I guess, right? Then the current helicity term will become about the same magnitude as the kinetic helicity term. Then the alpha basically becomes to 0 and cancel out, right? So then this is what we do. So we carry out 2 more simulations rather than the Yuhong's already 14 and 16 simulation. Then, but we are not going to the higher resolution, but we actually go to the lower resolution. So going to lower resolution means actually the Reynolds number is going down. So it's going to smaller. It becomes smaller. So this is what we do. So we go in lower resolution and we got 2 more simulation. So this is the Reynolds number, so going down, and this is the proton number. So I calculate all this number using the same method in Hotelsang's paper. So like this one. So compared to this, so they are low media. So their low media Reynolds number is this. So it's roughly like this one. And so, but of course they are high case. The Reynolds number is very high, and so also even Yuhong's 16 paper is only just over 500. And but interesting is what we got is here. It's actually we reproduce the phenomena reported in the Hotelsang's paper by going to low resolution. You see, so this is Yuhong's 16 paper, and this is a 14 paper. And if we go to lower resolution, you see here the dynamo sort of disappear, and then it reappear again, right? So this is from the Reynolds number going to from high to low. But if I turn it around, you see, I just change the order of presentation. So here A, B, C, D. So is from Reynolds number going from low to high, right? So this C and D is now, this is the Yuhong's 14 paper, and this is Yuhong's 16 paper. So you see, this is exactly look like what Hotelsang's paper found. So dynamo with the increase of Reynolds number, dynamo first appear and then disappear and then recover, right? So basically, I think I prove that actually the Yuhong's 14 and 16 paper is already in the recovered phase. It's already in the recovered phase. What this Hotelsang paper stated. So this is just a show this plot. So let's look at all these numbers. So basically, we just following like what Hotelsang calculate all these not only this proton Reynolds number, proton number, but also the turbulence energy and the mean magnetic field energy. So basically, in their paper, they say that the turbulent energy is always increasing with the increase of Reynolds number. It's the same here as ours. So the turbulence energy is always increasing. And what they say that the mean field energy is first decrease by this percentage, and then increase by this percentage. And in our case, we also see the decrease by this percentage, and then increase by this percentage. So it's all the same, it's all the similar. So even the percentage number is not the same, but this decrease and increase is all there. So okay, and also what is the most interesting to me is that it indeed in the case where the large scale magnetic field disappears, the kinetic elasticity and the current elasticity term cancel each other near the bottom of the convection zone. So these two lines, this 16 and 14, we already see that. So you see this dotted line is the case where the dynamo disappear. You see this blue dotted line is here, and the red dotted line is here. So in here, this is the resultant. This is calculated the alpha coefficients using this formula. So you see here, indeed, that near the bottom convection zone where the case dynamo disappear, indeed that the alpha, the resultant alpha between these two, from these two terms, they cancel each other. Here is going to the 0. So you can see that is actually when the dynamo first appear, it is actually in this range. The result alpha is negative and then disappear, go to 0. And when it reappear, the alpha becomes positive near the bottom of the convection zone. So this, so we use this formula, nicely interpreted why, we see this dynamo first appear and then disappear and then disappear and then recover again. And also this, this, because Hotterson first reported this phenomenon, then I go to ask him to give me all his numerical data, and then I calculate all this current helicity and kinetic helicity in his data. And we found that exactly is the case also in Hotterson's numerical data. So if you look at this is the current helicity, but here the red line is the current helicity for the high case, but I divided it by 10 because their current helicity is is very large. So if I want to put it in the same frame, so I divided it by 10. So here you see their current helicity high case, and this their kinetic helicity. And this is so if we so this is the same, but we here we make plotted only in the near the low. Near the bottom of convection zone, so make you see a little bit more clearly. But anyway, this is the resultant alpha calculated from this formula, and you see exactly here. Here, this is the blue line is the low case. This is the medium case where the which is the case that the dynamo disappear, and here the red line. This the alpha. This alpha is already divided by 20. So basically the real alpha is way here. So you see here alpha is here. So it's actually exactly the same. So in the low case, the alpha near the bottom of convection zone is actually negative. And here they cancel each other. So can basically go to the 0, and then this become positive again. So all determined, actually says this formula is correct, and this term is important. So why I try to, what I really want to inference here is actually because of this formula and because of our simulation and hierarchy simulation, because what I want to analyze is actually at the high Reynolds numbers, and the role of current helicity actually dominance over the kinetic helicity, as it is already in these two papers simulations, and of course also in the high case in Hideaki-san's simulation. And then as we further speculate that in the real stuff where the Reynolds number is extremely high, so even for Hideaki-san's Hotterson's simulation, his Reynolds number is about 2K, it's nearly 2K, and but the real sound, the Reynolds number should be even higher than that, and but so we speculate that in the real sound, the current helicity may actually play an overwhelming role, and the role of kinetic helicity as the only concern in the conventional kinematic mean field theory may have become ignorable. So this really what I'm trying to say for this, and but also this just because this question. So basically, I think this what we are saying is not too much different from what Yu Hong and also Hideaki-san, they have inference. Basically, they have inference that's the role of small scale magnetic field. So this plot is from Hotterson's paper. Basically, what they found is that at the small scale, so ILO is larger than 40, whereas 40 is actually the magnetic energy exceeding the kinetic energy in their high case. So where the high case have Reynolds number like this one. So that means their high case is in the super partition regime, and but in our case, so even in the this is a similar plot for our simulations. So even for the Yuhong's 16 simulation, so you see here in the for the small scale field, the kinetic helicity. So this dotted line of kinetic helicity, the solid line is kinetic helicity, and dotted line is magnetic helicity. So they roughly just got equivalent. So that means for this case, the kinetic is roughly the equal partition. So equal partition. So we have not reached the super partition yet. But even for this, you see here, this is the current helicity. So this dotted line is the current helicity, and this solid line is kinetic helicity term. So you see here, for this the 16 case, the current helicity term is dominant over almost all in the all case. So except for the L equal to 1. So from L equal to 2, so the current helicity term is already dominant over the kinetic helicity term. So that means the current helicity actually dominates over kinetic helicity at a much lower Reynolds number compared to that of the magnetic energy to dominant over the kinetic energy. So I'm trying to say that is even though in our simulation for the highest Reynolds number case, our magnetic energy and the kinetic energy are roughly the same order, but the current helicity has long dominant over the kinetic helicity over almost all scales. So that's the point. So it's still the role of the small scale magnetic field, but because the alpha is controlled by the current helicity and the kinetic helicity, and the current helicity is much more easier to dominate over the kinetic helicity. So this is the concluding remarks of this first part. So we found that there are depth variation of both current helicity and the kinetic helicity in the convection zone, and with the increase of Reynolds numbers, the current helicity actually plays a more and more important role, and the competition between current helicity and kinetic helicity near the bottom of the convection zone produced the disappear and recover phenomena reported in Hodgson's 16 paper. So that's the first part. So then the second part is
I have a question. I suppose you inject energy in that system through convection.
So yeah, yes. So I don't purposely inject any energy, So it's not it's not forced turbulence or something like that, but it's all self-produced. Yeah, self-excited turbulence and convection.
It's really diffusion. There's an energy transfer.
Okay, so at what scale is it?
Oh, it's the depth of convection.
No, but they have an entropy difference. So the convection is thermal, is the thermal heating at the bottom driven, but we don't insert any turbulence, forced turbulence or things like that. So basically it's all self.
Can you associate a scale at which you inject energy, or is it at all scales?
Inject no, we have a differential rotation. So actually energy come from the rotation or you could say differential rotation, but it's not we manually inject. So basically you have rotation and you solve the MT electric MHD equation, and so yeah.
There's a radiative diffusion that's driving energy, and that one's not.
Drive convection, not the energy.
There's radiative diffusion transport, and that is creating a convergence of thermal energy because of the temperature gradient in convection. So yeah, the scale, I think that is on the order of the depth of convection. So
Because I was wondering whether there was room for magnetic helicity cascade. Have you looked at magnetic helicity itself?
No, not yet. So, but
It'd be interesting.
Yeah.
Because it might play a role in that exchange of dominance of one over the other.
Yeah, I can, yeah, okay. Okay, so the second part is, so basically I because we already have these four simulations, then I extrapolated the mean field coefficients and try to analyze these coefficients and my main focus is what's the important role of these magnetic terms, So because so basically the method I extrapolating the mean field coefficients in dynamo simulation. So I just follow this paper, and so see. Oh, but this paper also is from this paper. So basically I follow their method. So basically this is the definition of this EMF, and so and all these coefficients is alpha, beta, gamma, and so in spherical geometry it is this very complicated. So basically this summer, this 2018 summer, I spent almost a whole summer to rederive all these formula and so got things work. So basically we follow their method is actually we calculated in simulation. So what at each time, at each position, what's the EMF, and then we have this EMF, and so this is the Y, and this X is all this mean field and directivity, and then so this is the coefficients we are interested in, and so with this method to get the minimum these, and so basically to get all these coefficients. So this method what we described in this paper, and so basically this is what we found. So then I extract all these or 4Ks. So this is all low. I call it low resolution 2, and this is the low resolution. So this is the case where the dynamo disappear, and so this is Yuhong's 14 paper and 16 paper. So here this for this row alpha R. So alpha in the R direction. So alpha, this is a matrix. So we mainly interested in this alpha theta phi. So this is alpha R. So alpha theta alpha phi. So this I display basically almost in the whole range. So it's in this range. But if I shrink the range and make it more like positive and negative. So you can see here. So this is the mainly positive in the southern hemisphere, and this is the black is the negative. So this is again. So again, this is in alpha direction. This is theta direction, and this is in the phi direction. So I just present what we extrapolate here. But what my main interest is actually I also calculate this alpha map using this formula, right? So I can calculate the map using this formula. And so this is what I got from this formula. So this alpha R theta phi. And but basically what I really want to show is this slice. So here this in the top here is what we extrapolate for the 4 cases. And here you see is what I calculate. Yeah, of course also using from the simulation data using this formula. And here this one is I calculated the alpha if I drop this kinetic term only using this current helicity term, and this one is I drop this current helicity term only using this kinetic helicity term. So and I also just shrink the range to just so now I'm just maybe mainly care of it's positive or negative. So you can see here, if traditionally we only consider this term, right? Kinetic term. If you look at here, so let's say the southern hemisphere it is positive, it's positive near the bottom, and it's negative in the upper convection zone, right? And but if you look at the what we extrapolate, you see here, so mainly it is positive, right? It's positive one. No, here is just opposite. This is negative. This is negative, right? And but if you look at the chemical term, so here you see they have opposite sign, right? So here this is the positive and this is negative, and this is what we got, these two terms together. Then it becomes this like this one, like this positive one again. And so you see here, if you compare this with this, so it with this, so this will, you see here, this is negative, and this is negative, and this is positive, and but if you compare these two, this is positive again, and if you look at here, it is only the positive, right? So that means if you use only kinetic helicity term, you may even got the wrong sign, right? But if you use the current helicity term, so near the bottom it is correct, but near the surface it is not correct. But if you use the two terms altogether, it goes most likely, what we extrapolate from the simulation data. So that means actually you really need to consider the current helicity term and put them together to make it is most likely the what we extrapolate from the real simulation. So this is just another way to present it. So to present it what I just said. So the yellow means that they have the same sign, and the blue means they have the opposite sign between this calculated alpha and this extrapolate. So you see here, if I use these two terms altogether, it will have the most more yellow reasons than if I use only the current helicity term or only the kinetic helicity term. Particularly if I use only kinetic helicity term, so you see here to have particularly for the low case, you have a lot of blue reasons. That means that even your sign is not correct. So that means this term is really important. And also, I can calculate the alpha maps. So during the circle maximum and the circle minimum, right? So by circle, because all simulations don't really have very, they don't have butterfly diagram. So but we have circle, the maximum and the minimums. So what I define maximum is actually, so if I calculate at each moment, I calculate with the mean Toyolado field. If the mean the magnitude of Toyolado field, and if it is larger than a number, then I define it as the maximum. And if it is smaller than a number, then I call it is minimum. So basically, then I extrapolate all these coefficients only using the maximum data points, and so this one is only using the minimum data points. So that means I have a way to separate what's the alpha map during the maximum period and what's the alpha map during the minimum period. So basically, when I do this, I want to check this formula. So this is a very, quite very frankly use the formula for the alpha quenching. And so basically, they assume that during the maximum where the mean B is larger, so the alpha should be smaller, right? By this formula. This is what usually people use for quenching of alpha. And but if you look at this, so basically, so this is for the 16 case. So this is the black, this this black thick black line, thick line is for the maximum. So and this line is for the minimum. Here, so I didn't average all regions. I only average so between these 20 to 35 degrees. So this is the region where the field is the strongest. So that makes this more evident. So basically, if you look at this, this is the maximum. So this is the variation with the solar radius. So this, you see, this is the maximum, and this is the minimum. So here near the bottom of convection zone, so indeed that during the maximum, the alpha is smaller, right? And also near the surface is also the during the maximum alpha is smaller. But in the majority of the convection zone, you see here the alpha value is actually larger than during the maximum is actually larger than the minimum. So that means this formula is not always follow, not even quantitatively, because quantitatively that means to during the maximum, this alpha should be smaller, right? But even but at all these regions you see here, and the alpha value during the maximum is actually larger. It's not instead of smaller. So this is for the 16 case, and if you look at for the 14 case, so here you see here in these regions, again during the maximum, the alpha value is actually larger than during the minimum. So that put the question for us to use this formula for quenching, and so that's for the alpha. And also we can calculate the beta map, right? So this is what got extrapolated the beta maps. So for this is displayed in this range. So this is the range what we usually use for the turbulence diffusion, right? But it's around this number. But if I plot get in a shallow range, so like go to this range, display range into go this. So if you look at this is the 16. So you begin to see a lot of dot points, black dot points, right? Black means actually what the beta is actually negative. So this is more clear. So if I calculated the total beta, that means that's I average all these three components, and I got this from the low Reynolds number case to the high Reynolds number case. You see here in this case, you see a lot of black points, black dots near the bottom of the convection zone. That means in these regions, actually the beta is negative. So that's become very interesting, right? So beta negative means what? Because we also beta is we think beta represents diffusion, right? Diffusion should always be positive, right? Beta value, but now it becomes negative. That means it's instead of diffusion, it's actually becomes more concentrated. And also interesting is this is also the case in the hotter sun simulation data. And so if you look at this there, so his high case, of course this high case, you see almost the whole region is spread with all these black dots. So that means there in this the whole almost the whole region is becomes a negative beta. So that means it's very interesting is that so what that means negative beta means. So I go back to Anibal case paper, and I noticed this is a page cut from the paper, the conclusion page and conclusion page. So basically they said this they call alpha effect. So it's actually reaction to the of the residual of the energy and residual helicity. So basically, I think in their paper, and mostly may focus on this residual of this helicity. That means this then we have this formula, right? Taken from traditionally kinetic helicity to this formula, consider both kinetic helicity and current helicity. Then I wonder whether if we also relates to the residual energy, whether the beta is actually also determined by the difference between the kinetic energy and the magnetic energy. So nobody talk about that, but I got some has I think from this formula, and so maybe beta is also not only the kinetic energy but also divided by the magnetic energy, and so also because know that the meaning. If we have negative beta, that is have very significant meaning for the dynamo theory. So because it's not diffusion, you can have dynamo purely for negative beta, right? So that's like the beta effect. So let's look at the gamma map. Gamma. We can also actually the gamma map. But gamma is basically has a magnitude as velocity is like what we do call pumping velocity. So this is a pumping velocity for this r direction, and for the theta direction. This is for the phi direction. So again, if I just look at the black and white for the positive and negative. So if we just let's focus on the pumping velocity in the theta direction. So you see here. So this is at first this is the negative. So because the r positive is in this direction, so that means near the surface, indeed it is going to the pole, and then it become to the equator world at a very shallow layer, and it has a little bit going to the pole, a little bit in the high latitude, but in the low latitude is actually going to the equator, and you see, but here. And then I noticed, notice this exactly what the flux transport model needs, right? And so and then I also plot out this plasma velocity because so you see this plasma velocity. So here I compare, this is the pumping velocity, and this is the plasma velocity. If you look at like this plasma velocity is, this is, it's not that regular, and so but this we always see, people talk about there are multiple marine circle in the simulation, right? And observationally from the helioseismology, people also are talking about the multiple marine flows, right? But then what I found is that for the pumping velocity, it actually has the right shape that the flux transport model need. Right? So then I asked the question: so could the pumping velocity replace the role of marine flow in the flux transport dynamo model? Because for in our case, the magnitude of the pumping velocity is roughly the same, and it's right in the range that the flux transport model need. So or maybe they working together. So I think that's also interesting to learn from this analyzing of this pumping velocity. But the story may not be that simple, because I also calculate the pumping velocity in this ultrasound data, and again, it also shows nice, this circulation. But the difference that their pumping velocity is very small. It's much smaller than the marine flow velocity. So that means it's not likely for the pumping velocity work for the flux transport model in their simulation. So that's the question. So I'm not sure yet. So the concluding remarks of this part 2 is that, so by comparing the extrapolated mean field coefficients with those calculated from this formula, we confirm that the current list term plays an important role and should be included. And the small scale magnetic field and basically, I'm referring to the Canhelis term, doesn't always quenching the alpha coefficients. There are reasons that the alpha values are actually larger during the cycle maximum. So the quenching formula, like this one, may need to be reconsidered. And when the Reynolds number is large, and actually the beta coefficients could become negative, and the pumping velocity in the theta direction may, so I said may, so I'm not sure yet, may replace the role of marine flow in the flux transport model. So I stop here. So thank you for your attention.
Thank you for this interesting talk, May. And do we have any questions from the audience or from the online audience?
The plasma flow, that's the meridional flow.
Oh yeah, yes, yeah.
Flow.
Yeah, yes, this is the mirror flow. So yeah, the real plasma velocity, so V theta. Yeah. So this is the VR, V theta, V phi. So the middle is the V theta. V theta is the marine flow.
And then in Higgs, is it also similar to this as multi-cell in Higgs simulation in meridional flow?
Yes. So you see, it is also looks similar, but the magnitude is much smaller.
In meridional flow.
In
the plasma meridional flow.
Yeah. The pumping velocity is much smaller than the marine flow in Hodiaki's data, but in our simulation case, so these two are the magnitude are comparable.
If it's really working, then we should see the craterwood propagating. So
That's
yeah. Anyway.
No. That's
the pumping velocity. If it's really doing.
No. That's deep. There's something different. So I'll calculate later. Yeah, I calculate all these alpha. This marine. This butterfly diagram. So I did that calculation, but it's not conclusive. So I didn't present it.
We have a question online.
Oh. Hi.
Can you hear me?
Yes.
Okay. So I have two questions. First is I understood that you are using data from different simulations. And so my question is, those simulations, were they done with the same code, with the same numerical methods, but just different resolutions, or were those like different codes or different numerical methods, and so on? This is one question. And the second is simple. It's what is meant by explicit and implicit Reynolds number? You use this term, right?
Okay. Yeah.
Yeah. So I'd like to, because this can mean different things in different communities.
So basically, I mainly use the simulation data from using two code. One is what I call our simulation is using Yuhong's code.
It's elastic.
Yeah. Yes. And another part is Hidioki's code and simulation data. He is this reduced down speed code. So very different. So when I compare different cases within the simulation, so we use the same code. So the same code from or from low resolution to high resolution, and so this is compared within using the same code.
Okay. So what is the meaning of the implicit explicit Reynolds number?
Implicit. So this is go to there. Implicit. So basically, so it is let's say the Yuhong's 14 paper. So basically, in that he when he solved the equation, he has exploited resistivity in the formula in the MIT equation. Do I?
Yeah, one is the viscosity, uniform viscosity and magnetic resistivity. And then the other one lower, which is
Yeah.
the explicit one, so it's only the numerical.
Also, so wait a minute. So numerical viscosity is termed implicit or is so?
Yes, kind of implicit, these kind of.
So explicit, that means is you have explained the new impose explained the resistivity index.
In case we put in an explicit uniform viscosity and the magnetic diffusion, both.
Yeah, and
And then with the later simulation, we do that. So it's only numerical diffusion, grid-based
Okay,
numerical
okay.
diffusion.
So
So just trying to see what happens when you reduce numerical diffusion. Sorry, reduce the viscosity and also the magnetic diffusion. But it's very limited. Yeah. In
so
terms
now
of
when you answer my questions, I have a comment. May I say something? Yeah.
Yeah.
Okay, so I was involved in some simulations or solar simulations in the past, and my experience is that when you do dynamo in all those like solar activities, those results are sensitive to almost anything. You change something in the code and you get a different result. So the question is how really, the result that we get, how representative they are of physical situation or really of physics. Because I can probably simulate, lots of different things by changing resolutions, changing numerical methods, and all this stuff.
Yeah. Yes, exactly. So that's what we are trying to do. We want to, understand, this dynamo disappear and reappear phenomena, but in terms of, the computation between the current helicity and kinetic helicity. That's what means we are not only just reproduce Heliocoson's result, because we really understand why this is the case in terms of the physics and the underlying, right?
Okay, thank you.
Do we have any?
Oh, yeah.
Wondering whether the change of behavior that you observe in Matthias' computations and yours was linked to a different attractor, and then you have a bifurcation. I mean, I very vividly remember Arnold asking Georg Frisch to do a computation because in Russia they couldn't go further in Reynolds number. And this is exactly what happened in the framework of the ABC flow, the Beltrami highly helical flow. So I was wondering whether it was that change was due to the fact that you went somewhere else in parameter space, in configuration space, or whether it was more the type of explanation you give.
I don't know, but to me, I believe my explanation, and I think it is, all these pieces put together, right? Because this calculate, not only the dynamo disappear and reappear, but also it just exactly happen, the case, the disappear exactly happen when the current helicity and the magnetic term, have the same magnitude, right? So, and it is also in Hideaki's Hotoson's simulation data, which, they use a different code, numerical approach are very different, right? And but we got the similar results, right? Similar results, and we also analyze all these current helicity, kineticity, all show the same thing. So that's why I believe this, is true.
I have another remark, which is that the equivalent of eddy viscosity has been computed for magnetic resistivity within the framework of the closure you mentioned. But the difference with helicity is that beta works for the velocity field and beta m works for the magnetic energy. Whereas the helicity is a combination of the two. So I will have to go back to the paper and see whether I vaguely remember that the magnetic resistivity, turbulent magnetic resistivity is a bit different, but I have to double check the paper.
Yeah. Yeah. Oh, yeah. Mm.
Do you have any other questions? If not, let's thank our speakers again, and we'll see you next week.